All right, welcome everybody to the next session of the Colorado ENP Study Session Series. And tonight we're going to talk about location and GIS technology. And yes, I'm just as excited about it as I sound. So these study sessions are being brought to you by the Colorado 911 Resource Center, the Colorado 911 Training Standards Institute, and the Colorado 911 Program. And I know we have Connie, who is the Executive Director of the 911 Resource Center with us. Connie, do you have any words of wisdom for us before we dive in?
No words of wisdom, just welcome everybody and thank you for putting your time and effort into this.
Thanks, Connie. I'm so happy that we have so many people joining us live on Thursday nights for this. So thank you for choosing to spend your evenings with us wherever you are. And again, I just want to encourage everybody. The reason that we are doing these live is because we want the questions that come with a live study session. So don't be afraid to raise your hand or pipe in with a question. And I guarantee you, if you have a question, you're not going to be the only one, and your question will help other people who watch the recordings down the line. So don't be shy. And with that, we're just going to dive right in. So I will say that we are doing this in conjunction with the ENP study guide. And I put the section numbers at the top of each slide so you can follow along, but we're kind of jumping around today and kind of put them in the order that made sense to talk about them in conjunction with each other. So keep an eye on those. There's one where we take a hard left turn into a different section altogether, and I put some stars in the header for that so you could follow along. But if you have any questions, again, don't hesitate to ask. All right, what are we going to talk about? We're going to talk about GIS, Geographic Information Systems. So GIS is it's a kind of a long definition. So it's a collection of hardware, software, people, procedures, and data that tie together information, displayed graphically and stored within a database. And here we all thought that GIS was a map. Well, the end result of GIS is displayed in a map. But as you can see from that definition, there's a lot that goes into it beyond just the map. So again, it's hardware and software, people and procedures, and data. So all of those things together tie together some information that is displayed graphically in a map, and it's stored within a database. So GIS stores information that represents or is linked to a geographic location or a space on Earth. So that's commonly referred to as spatial data. So in other words, if I go into a GIS, what I'm looking for is data that's linked to a location. So right now where I'm sitting in Colorado, my house is a piece of data, basically. Where you are is a piece of data. And so each data set within the GIS could be considered a layer of similar information, okay? So you can have different data sets within the GIS, and all of those data sets come together to form that GIS. The nice thing is that GIS can relate unrelated information by using location as the key index variable. So in other words, I can put information about my house into a GIS, and it may seem unrelated. So I've got an address, but I also have a latitude and longitude, so a street address, a latitude and a longitude. I also might have information about this location that could be related to this point on the Earth. But all of that would come together in this GIS, and the location would be the key index variable. So the location is the common point. GIS is not a mapping program. So I know that when all of us think about GIS, we're thinking about the map. But GIS itself is not a mapping program. GIS is a complex mix of all this data management, database management, display technology, and analysis tools come together, and the way that you see it is in a map. Most information in a GIS is referenced to a location. So the nice thing is that you can use GIS for a lot of different things, as we're going to see. So in a GIS, the spatial data can be displayed as a point, as a line, or a polygon. So those are the three basic ways to represent geographic data. For example, the road that's outside my house might be represented as a line. Makes total sense, right? A road is a line. That fire hydrant might be represented by a point, and there actually is a fire hydrant in my yard, so that's a point. But there are other points that can be on my property, like the house, and anything else that I might want to represent as a point. The lake might be represented by a polygon. So there's a lake down the street. It's a little pond, and that pond might be represented by a polygon. So there are three basic ways to represent geographic data: a point, a line, or a polygon. Yeah, Daryl?
What's a polygon?
Well, a polygon is a shape having many sides. Do you have an example of a polygon, Mr. Dungeons and Dragons?
Well, any kind of shape could be a polygon, right?
Right.
Yeah.
Like a 20-sided die?
It's a two-dimensional shape rather than a one-dimensional shape would be a line.
Perfect. Actually, thank you for clarifying that. That is a great question. All right. So GIS can be used to visualize information that may not be otherwise apparent by analyzing the location of roads, intersections, schools, fire districts, and other features. So you can use GIS to analyze all kinds of data, and we're going to get into some examples of that. But the records in a database that describe the data layer are considered attribute information. So for example, if you go into Google Maps, and because I don't want copyright infringement, I did not put examples of this into the slide deck. But if you were to pull up Google Maps on your computer while we were talking, down at the bottom, you could choose different layers of the map. And those layers can have different attribute information. So you might have a road layer, and the road layer might have a street name, a street range, and emergency service number. Remember, we talked about ESNs last week, okay? So that's what an example of a road layer that might have. In Google Maps, you can also have a traffic layer, and if you click that layer on, then it overlays traffic patterns on that. One example of a data layer that drives me crazy every time I use it, in the winter, I like to decorate my house for the holidays, and I like to enter my house onto a local radio station's map of decorated houses so that people can come by and see it. Well, when I put my information, my address into that map, it thinks that I want to see other people's houses that are decorated, which I do, and it will put a layer of Christmas lights onto my Google Maps. And that is another example of a layer that can be in GIS. And then I have to figure out how to take it out every year. So that's just another example of a layer. So a GIS stores geographic information in a collection of layers that are stored for analysis and visualization. So you might see that in your CAD or your phone mapping as different layers. You could have a layer for response area boundaries. You can have a layer for anything that you want as long as it's built into your GIS. So when you're going to plan and build those GIS, some keys to successful planning are database design. So you need to have an idea of how you want to design that GIS database. You need to train your staff not only on how to build that GIS, but also how to use the GIS. You need to have high data quality. So garbage in, garbage out, or great data in, great data out definitely applies to your GIS. You need to have continual planning. A GIS is not something that you can build and then just leave. It can't be stagnant. It has to be constantly updated and planning for new layers and additions. You have to have a production of outputs. So once you build all of this, you need to make sure you have an output for your GIS. And poor planning can lead to a stagnant GIS or unusable data, loss of investment, and failure. Nobody wants that. So your keys to successful GIS are there on the screen. So when you're building a GIS, you need to determine the organizational needs prior to finalization of software, hardware, and system design. In other words, what do I want this GIS to do when it's completed? How am I going to use the GIS? And you'll see this come up in 911 a lot because maybe your county has a GIS data set already for the county, but is it sufficient for 911's needs? That answer might be yes, or that answer might be no. Now, when the county built that GIS, they might not have been considering 911's needs, and that's okay. And you could take that GIS data set and use it as the foundation for your 911. But if you're going to build a 911 GIS data set from the outset, then obviously you need to think about what am I going to use it for? And those organizational needs are going to determine what software you need, what hardware you need, and your system design. GIS planning involves managers developing and communicating the goals and objectives of their department and the desired outputs. They also must determine their GIS needs from the beginning and to continue to develop goals once a GIS is established in order to have a successful program. So again, once you have your GIS data set, you need to be constantly making sure you're updating it because nothing stays the same in 911 and nothing stays the same out there in the world either because everybody's constantly building subdivisions and new buildings, and sometimes they change street names and so on and so forth. So I'll just pause there and see if anybody has any questions so far. The polygon question was great. So who else has questions? Okay. So as we said, data accuracy is critical for reliable query results, data modeling, and visualization. So this is an example of a map, right? Because when you're thinking about, okay, how do I build this GIS? Well, you're going to get data from someplace, and that data can come from a wide variety of sources and formats. I won't make you raise your hands, but I know there's several people who are live on the call who were taught how to read a paper map. Well, that can be a source of data when you're building your GIS. So, and actually in the past, that geographic information was transmitted via paper maps. But today, those hard copy maps can contribute substantially as a data source. So many organizations start by scanning or digitizing paper maps into the GIS program. And this allows GIS users to geographically link data and tag each feature with the appropriate attribute information. So if I was going to start with this map of Denver, or if I wanted to start with a map of my neighborhood, I would scan that paper map in, and then I would make each address a point, right? I would make each road a line, and I would make those ponds and those other features maybe a polygon. I can also make anything else a polygon. It's just important to understand that, you know, that's a type of element within that GIS. So then I could take and geographically link that data and then tag each feature with the appropriate attribute information. Other ways of building GIS data sets are GPS technology, aerial photography, satellite imagery, surveying descriptions, and other existing data to create those data layers for your GIS. So once you have that data, the data resides in the GIS storage system where the information is available for querying, analysis, and production. So you might not know, but you can use GIS for a lot of data analysis. And we're going to see that in the future slides. It's much more than just locating yourself on a map or locating someone on a map and then trying to route other people to them. The advantage of a GIS is the ability to compare and analyze, symbolize, measure, and get answers from the data. I bet you didn't know GIS could do all of that. So for example, finding all the houses within 1 mile of an emergency incident to generate a list of addresses needing contact. So the folks out in California could be using that to help build those addresses where they might need to go and evacuate people from the fires, just as an example. All right, so what is metadata? Besides being a fun word to say, metadata is a summary document providing content, quality, type, creation, and spatial information about existing data sets. So you've got your data set, And the metadata is like the data down deep below the top layer of data. So metadata may describe and document its subject matter. So maybe you want to know how and when and where and by whom the data was collected. So if I want to embed metadata into my GIS data set, I would go in and say, okay, well, we created this data set by uploading this map, and it was done on this date and by this person, right? Maybe you want to describe and document the availability, who the GIS has been distributed to, its projection, what the scale is, the resolution and accuracy, and reliability with a standard. You can do all of that with metadata in your GIS layer. Did we have a question? Okay, so metadata consists of properties and documentation. So the properties are derived from the data source. For example, you might want to list what coordinate system and projection of the data is in that data set, and that would be a property. Documentation is entered by a person. So for example, keywords used to describe the data. So if I wanted to put a address, like if I wanted to use the word address as a keyword, that would be a form of documentation. So by creating that metadata and sharing it with others, then that information about existing data becomes readily available while providing that critical information about the data itself, including its limitations, vintage, and reliability. So for example, you created your GIS data set, you uploaded it into your system, and you want to make sure that future employees or future people who are going to use it know exactly who created it and using what standard and so on and so forth. Well, instead of keeping that in some spreadsheet somewhere or some document that might get lost to time, you can create that metadata and put it directly in your data set so that it goes with that GIS data set wherever it goes. So the metadata makes data discovery easier and it reduces data duplication. So why do we use GIS in 911? Well, one main reason for GIS is to geolocate the alley caller location, whether it's an address or a coordinate from wireless device against other related information. So the databases in GIS allow for a quick, efficient searching through all the information to provide answers to questions like, where's the nearest hospital to this caller? What's the closest police unit to this incident? Which agency responds to calls in this area? What's the fastest route to this incident? This can all be done using GIS, and it can be done quickly. So the answers to those questions can be displayed on maps. It can be sent to other applications such as CAD, or it can be stored for future analysis. So for support of 911 mapping, a GIS usually consists of, but is not limited to, street networks, ESN boundaries, cell towers, PSAP boundaries, hydrology features, addresses, and railroads. And each feature is representing some sort of spatial data with attributes that's made graphically available to the telecommunicator. Now, my guess is that most of you on this study session are already using mapping that is supported by GIS, either in your CAD or your phone system or other systems that you might have available to you in the PSAP. You just might not have known that it was GIS supported. So you can use accurate and current spatial databases. They can be used by all public safety agencies to increase efficiencies. So for example, law enforcement can use GIS data for geoprofiling of criminal activity. Like you can create, using GIS, you can create a map of hotspots or frequent areas of crime. Obviously, as a dispatcher, you carry that around in your head, but the cops can use GIS to generate that. They can use GIS to determine areas that need increased law enforcement presence, locations for new stations, identifying crime trends, et cetera, et cetera. Fire agencies and EMS agencies can use it for the same types of things. Another benefit to 911 is using GIS updates to drive those MSAG changes. So remember in the last session, we said that GIS and MSAGs were going to exist side by side for quite a while we make those transitions. But the nice thing is once you have an accurate GIS established, the changes that are made to MSAG should be a result of a change made in the GIS. So you update the GIS and then you can use that GIS data to update your MSAG. But the benefits of coordinated MSAG and GIS include validation of information via a one-to-one match between the street name, the ESN, the community, and the range. And after the GIS and the MSAG are coordinated, your landline call should map more accurately and confidence will rise for the mapping deployment at the PSAP, which is great. It's nice to be able to trust the map, right? One way to ensure a match between GIS and MSAG is to geocode the Annie database to an address point file or a street center line file in the GIS. So you can imagine how much work it takes to go through that MSAG or that Annie database, right? And geocode every single piece of data in that MSAG and that Annie database to an address point file or a street center line file. It's painstaking work, but once you get it done, the errors that show up as a result from geocoding will enable that GIS analyst to determine the discrepancies so that they can make their mapping more accurate. So again, if you know anybody who's looking for job security for life, public safety GIS, really good job to go into because everything in the 911 future is about GIS. In NextGen 911, the GIS is going to become the central data store, or one of them. It'll replace the traditional tabular MSAG with spatial analysis to determine call routing. So instead of that call routing where it queries the MSAG to get that location, it's going to use GIS to determine call routing instead. And so through that, GIS has moved from being a tool that determines jurisdictional boundaries, although it does that, but it also provides real-time emergency request routing. So within that NextGen 911 configuration, accurate road centerline and ranges, PSAP boundaries, and emergency services boundaries are required GIS data sets for deployment and operation in a NextGen 911 environment. So depending on which state you're watching this from, you know, there are some states in the country that have already moved to a full NextGen 911 environment, and they have these GIS data sets with accurate road center lines, with accurate PSAP boundaries, with emergency services boundaries. You have to have all of those data sets in order to operate in a fully NextGen 911 environment. Here in 2025 in Colorado, we're still working on that, but there will be a day when we can get to the point where we have all of those things and we will be in a closer to a full NextGen 911 environment. So I'm going to stop and see who has questions.
Jennifer, I might have missed this, but what does MSAG stand for?
Thanks. Master Street Addressing Guide. So we talk about MSAG or Master Street Addressing Guides in the previous study session, but it is a tabular database. Tabular meaning it has columns and rows. It's a tabular database of all of your addresses within your PSAP area. Does that make sense?
Yes, thank you.
Sorry, thank you so much for asking. Who else has questions? That was a good one. All right. So these GIS layers have to be available in the NextGen 911 environment so that the eSurf or emergency call routing function and LVF or location validation function, those have to be available for those two things to work. And it's required for those selective transfer call handling features that are GIS based. That's a fancy way of saying that the things that happen in legacy call routing, in order for them to happen in the NextGen 911 environment, those GIS layers have to be there so that those GIS based call routing functions can work. So the same authoritative GIS should be provisioned for all NextGen 911 functions via the spatial interface and continually maintained as changes occur. That authoritative GIS should also be used for all other applications using GIS in the PSAP, such as CAD and map displays and AVLs, etc. When I say authoritative GIS, just keep in mind, and we're going to talk about this a little bit later when we talk about apps that can find you versus 911 that maybe has trouble finding you. Authoritative means that this is a GIS data set that meets a standard for 911. And oh man, look there at the bottom of the screen, there's your standard. So authoritative GIS means that it has met those rigorous standards and can be used for 911 purposes. So if you want to read more about that, that's the data standard there, and you can go look that up. And it's a little light reading for you, but we're not going to go through it today. All right, so what is geocoding? Not the same as geocaching, but you can use things that have been geocoded to go geocaching if you want. Geocoding is the process of assigning geographic coordinates, i.e. latitude and longitude, to tabular data stored with addresses. So as a review, tabular means data consisting of or presented in columns and tables. So if you were in last week's study session, we talked about the MSAG and showed a visual representation of each address showing up as a line in a spreadsheet that has information about that address, right? And it has the pre and post directional and the street name and the street number or the house number and so on and so forth. So geocoding is the act of taking, for example, that master street addressing guide and assigning geographic coordinates to each piece of tabular data stored with the address. It's a lot. But when you're geocoding, it gives a spatial location to that data that doesn't otherwise have one, which can then be mapped and entered into the GIS. So for example, if you take the alley database, you geocode the table to an existing street centerline file. So the result is a data set that has customer names and telephone numbers that are linked to coordinates in a GIS, and those would be represented as points. So for example, my address exists in an MSAG, say for the county that I live in, right? So I have it in my brain as my address existing on a line in a spreadsheet. And if it's geocoded, if someone's going to build that GIS data set, they're going to come along and they're going to mark my address on that spreadsheet, and they're going to say, okay, well, this address is at such and such latitude and such longitude, and I'm going to make that a point in my GIS data set. And boom, they've geocoded my address over and over and over for the entire alley database. So for those of you who are better at visual learners than audio, here's an example on the screen. So if you have an address of 549 Denise Drive and it has an ESN or emergency service number of 340. So the corresponding line in the GIS for Denise Drive has an assigned address range from 500 to 599. So you've got a line, right? Envision your street as a line, and the assigned address range is 500 to 599. So on this particular street, the even numbered addresses fall on the west side and the odd numbered addresses fall on the east side, on the other side. So after geocoding, 549 Denise Drive is going to be located halfway along the segment on the east side of the street. So you map a point at that location along the street. Maybe it's offset some distance to the east of the street center line because generally your house is not like right on the street center. It's set back from the street center. So you map that point along that location, offset some distance to the east of the street center line. And that's geocoding for that address. What happens if that address exists in other cities? Because we never see communities use the same street names and numbers because they're always coordinated, right? No. Addresses exist in other cities all the time, and that could be the case for your jurisdiction as well. So if you dispatch from multiple cities, then you've probably got duplicate addresses. So you want to make sure that you're geocoding, and it would use that ESN or other community identified, such as the city or community name, to distinguish that multiple address locations within the database. So not only are you going to geocode to say, this is the latitude and longitude, but you're also going to attach an ESN to that point, and you might attach that community name to that point as well. And of course, because we're all humans, sometimes errors occur. You might have inaccurate GIS street address ranges or names. You might have inconsistent definitions with local naming messages or methods. So for example, in the book, they give the example of James Street Drive. Well, what if James Street is the street name? So you wouldn't say it's James Street Drive, because the people who make up addresses, sometimes I don't know what's going on in their head. So that could be an error. And then interpolation assumes that assigned addresses are evenly distributed along the length of a segment. And in reality, this is almost never true. So if you're thinking about an aerial view of a neighborhood, right? And you're looking at all the little houses on a street, and you're like, oh, well, these are all evenly distributed along the length of the street. That's not the case in reality. So those lack of evenly distributed points can cause errors. All right. That concludes our conversation specifically about GIS, and we're going to move into latitude and longitude. So who has questions about GIS that we haven't answered so far? Are we good? All right, let's talk about latitude and longitude. So we're in 3.9.6 in the book. So E911 Wireless Phase 2 introduced latitude and longitude to the ALI response message. In other words, prior to Phase 2, those ALI and ANI responses didn't have any lat-long information in them. But the FCC mandate required wireless carriers to locate their callers by providing the longitude and latitude of the caller's location to the ALI database. So the PSAP has to have call handling equipment that can display that X and Y data. Yes, there are some PSAPs that do not have call handling equipment that that display that latitude and longitude. But if it doesn't come in, then it's going to give the cell tower address, which is referred to as Phase 1. Now, the vast majority of PSAPs have call handling equipment that can display the XY data, and sometimes you also get the cell tower address, but the lat and long, or the long and latitude in a Phase 2 environment should be the actual location of the caller. We all know that's how it's supposed to work. Doesn't actually always work that way, but you know, in an ideal world. So the longitude and latitude are the coordinates by which you can locate any point on Earth. And I swear the book says this all, so I didn't make this up, but people always say lat and long and X and Y, but latitude is not the X coordinate and longitude is not the Y coordinate, it's opposite. So if you say lat long, what you're really saying is YX, but that doesn't sound right in anybody's head, and that's not what people say. So everybody does it, but it's just good to know that when you say lat long, you're saying YX. Kind of funny. So latitude, lines of latitude are called parallels, and latitude is the Y coordinate, as we just learned. So latitudes are 180 equally spaced circles running parallel around the Earth, and they are numbered from 0 to 90 degrees, starting at the equator, going toward each pole. So they're measured along the y-axis from the equator. So any point north of the equator has a positive value, and any point south of the equator has a negative value. So if you look at this depiction of the Earth in a flat way, so you can kind of see it, the coordinate values are preceded by a plus or a minus sign. So as you can see, that equator runs right through the middle there of the map, and every area in the United States and Canada is going to have a plus latitude or a positive latitude or Y coordinate because it's above the equator. It's north of the equator. So for example, the Denver lat and long, see, I even did it when I was writing this out, are 39.742043 north, and it's positive. We'll get to longitude in a minute. Any point on the equator has a latitude of 0. So the North Pole is plus 90 and the South Pole is negative 90. Each degree of latitude is divided into 60 equal parts called minutes, and each minute can further be divided into 60 seconds. But in Enhanced 911 Wireless Phase 2, we don't care about minutes and seconds. We only care about the coordinate values. So on the surface of the Earth, 1 degree of latitude is roughly 69 miles, but because the Earth is not a perfect sphere, the distances get slightly greater as you go closer to the poles. Nothing's perfect. Now the longitude are called, lines of longitude are called meridians, and longitude is the x-coordinate. So lines of longitude are 360 equally spaced lines running north to south from pole to pole. And the numbers from 0 to 180 degrees start at the prime meridian going east and west. So what's the prime meridian? Longitude, or the x-coordinate, is the distance from the prime meridian, which is in Greenwich, England, a borough of London. I'm sure there's a fascinating story about why they picked Greenwich. Maybe someone wants to share that at the end of the study session, but that's where it is. So the Earth is divided into 2 parts or hemispheres of east and west longitude. So if you think of the Earth as a globe divided into 360 equal slices, you have 180 of those west and 180 of those east of Greenwich. So the lines between the slices on the globe are called meridians, thus the term prime meridian for the meridian that is the starting point, which is represented by all zeros. So all points along the prime meridian have a longitude of 0. So here is that same map representing or depicting longitude, okay? It's measured along the x-axis and is the distance from the prime meridian. So any point east of the prime meridian will have a positive value, and any point west of the prime meridian has a negative value. So again, that Denver Latin long has a negative value of negative 104.991531 west, because we are west of the prime meridian. I get it's a globe. At some point you just go all the way around, but that's the way it is. So just have to learn it that way. All areas within the United States and Canada will have a negative longitude or x-coordinate. And the space between 2 meridians is greatest at the equator, about 69 miles. This space narrows as it approaches the north and south poles, so the distance between the meridians is not constant. And in order to show you what I mean, I'm going to go back a couple of slides so you can see how this is. You can see that the distance between the meridians is greatest at the the biggest part of the globe, and of course it gets smaller the closer you get to the poles. So, who has questions about latitude and longitude? Yeah, Daryl?
Jennifer, would you say that in our part of the world, latitude should be like your attitude and always positive?
You can go with that if you want to. It's a great way to remember it, actually.
That's actually where I was getting at, is that it's a good way to remember which number is which. The one that's positive is going to be latitude, because like your attitude, it's always positive.
I love it. I'm going to think about that for the rest of my days whenever I think about latitude. Thank you. Michael?
I will never forget that either, but in case it helps anyone, my mnemonic is latitude are lateral lines and longitude are the long up and down lines.
I love it. I'm going to be thinking about Latin long and how it's backwards for the rest of my days. Those are some great ways to remember that. Anybody else? This is why we're doing it live. All right. So if you want to read some other standards for GIS in 911, then you need to go to the study guide and check out section 3.9.9. Now we're going to talk about other location determination technologies, okay? And so you can see that we're back in the in section 2, and we're in 2.3 of the study guide. So we're going to talk about other location determination technologies. They fall into 3 different categories. So handset based, as in it's based in my phone. Network based, meaning it's based in my cell carrier network. And a device based hybrid, where it's a combination of located in the device, but also the network based. So the FCC specified different accuracy criteria for handset-based and network-based technology, and the handset-based accuracy requirements are more stringent. But these distinctions are blurring as the FCC defines more strict criteria for determining the location of a 911 caller. So as you can imagine, when cell phones became prevalent, the FCC had to catch up and make some rules about location accuracy. And it always takes government a little bit of time to catch up with the pace of technology. So that's why you'll see a progression of FCC actions talking about accuracy or location accuracy. So the first one is the FCC's 4th report and order on location accuracy, which define the criteria for indoor location accuracy. So it's not enough to be able to find you out on the street. It has to be able to find you in a building. But in general, handset-based location technologies incorporate GPS, whereas network-based technologies use triangulation. And those device-based hybrids use a mix of location technologies available to the device. So when this book was written in 2020, the statement, wireless carriers that originally implemented network-based solutions are transitioning to handset-based and device-based hybrid technologies. I would imagine that's still true today. So while location services used for 911 use the same underlying technologies that are used for commercial mobile applications, think your pizza delivery and other stuff, but they operate in a slightly different manner than in the 911 environment. For example, they're required to provide a higher level of mathematical confidence than commercial location services, which may make location services used for 911 appear less accurate than a comparable measurement used for commercial application. I swear that's what the book says. It doesn't make a whole lot of sense in my brain, but okay. But users also generally have a higher degree of privacy when location services are used for 911 than for commercial mobile applications. So if you think about it, 911, governmental, it's okay, I guess, if, this location-based service that I'm trying to order a pizza, right? I should expect higher privacy I should expect a higher degree of privacy when I'm calling 911 than I am from the pizza place. So location services technology uses various location methods available to that device, including Wi-Fi access points, assisted global navigation satellite system, there's a mouthful, AGNSS or GPS, and some handset-based sensors. So 2 examples of device-based hybrid, that's what DBH stands for. 2 examples of device-based hybrid location technology are hybridized emergency location, or HELO, which was developed by Apple for its devices, and emergency location service, or ELS, developed by Google for Android operating system devices, because we can't just have one for all cell phones. It has to be proprietary for those device makers, of course. Most 911 calls are placed from mobile devices as of 2020, over 80%. And an increasing proportion of those devices use location services to provide those caller location. But the significant challenge for 911 is that methods used to determine caller location are proprietary, as we just saw, the difference between Apple and Android, developed by a small number of mobile operating system providers and entirely outside of 911's control. However, these technologies enjoy a global economy of scale, which means they're undergoing constant improvements, which benefits 911. So there's some upside to that. So let's talk about GPS. GPS was developed by the Department of Defense as a worldwide navigation and positioning tool. So the GPS system relies on more than 30 satellites that orbit at over approximately, that is not the right number here. That needs to get a, it's 12,600 miles out. Did I go backwards on a screen? Here we go. Yeah. Take out that extra zero. It's 12,600 miles from the Earth to serve as reference points for those ground receivers. So you've got the satellites circling the Earth. They're approximately 12,600 miles away from the Earth, okay? They serve as reference points for ground receivers. So GPS works by calculating the travel time of a signal from the satellite to the receiver. That travel time is measured and translated to distance. So that you can take those measurements from at least 4 different satellites. The latitude, longitude, altitude, course, and speed can be calculated, and that determines your location. There is some error in the calculation due to natural and man-made errors, i.e. there can be some satellite clock errors, imperfect orbits, and atmospheric conditions. So it's not a perfect system, but in general, that's the way it works. Now, when I said that we were going to jump back and forth, the book in that section from 2.13.2 says, for more information on GPS, go to this section. So I went to this section. That's 3.10. So 3.10 goes a little bit more into GPS system, and it says a little bit of the same thing. You've got more than 30 satellites, which they call the space segment, which makes sense. Your satellites are in space, and related ground stations. So the ground stations are called the control segment. There's one more segment we're going to see in a minute. So you've got the space segment of the GPS, and you have the ground segment of the GPS. So each satellite weighs 3,500 pounds. You don't want it to drop on you. The orbits are scheduled so that anytime and anywhere, at least 4 satellites are visible in the sky. Why at least 4? Well, we just learned that you need at least 4 to calculate an accurate location. Those ground receivers use those measurements from different satellites to calculate the latitude, longitude, altitude, course, and speed. The receivers, which is the user segment, communicate with 4 or more satellites using trilateration, which is a method of determining relative positions of objects using intersections of 3 or more spheres to determine locations on Earth. Wow, that's a lot of words. Basically, in order to find the GPS location of this cell phone, it needs to be able to communicate with 4 or more satellites so that it can use trilateration to determine my position of this object on Earth, okay? And in order to determine a fixed location, a GPS receiver has to know 2 items: the location of the fixed point and the distance to 3 satellites above the horizon. That's a lot of technology going into finding my cell phone or find my iPhone. If more satellites are available, then the accuracy is improved and the altitude information becomes more precise, which is why it works better when you're outside than it is inside. GPS receivers determine location and distance to satellites by interpreting 2 types of radio signals that are transmitted from each satellite in high and low frequencies. So if you have a higher priced GPS unit, they usually have multiple receivers, allowing for reception of signals from satellites simultaneously. So the more you pay for your GPS, the more likely it is that it has multiple receivers, so it can receive signals from a bunch of different satellites. The receiver measures distance by timing the signal from the satellite to the receiver. So you use GPS technology in cell phones, cars, boats, planes, farming equipment, cop cars, etc., etc. But in 911 call delivery, GPS-enabled handset phones play a vital role in the location of a wireless 911 caller. The differential GPS relies on a calculation from a second terrestrial receiver at a known fixed location to the satellite, and then compares it to the first calculation to determine the error in the signal. So you might have public safety using DGPS for vehicle and resource location. So in general, standalone GPS, everything that I just spent time explaining to you, standalone GPS and DGPS are not used in the 911 space because a GPS has been adopted. And you're like, oh my gosh, okay, so what is a GPS? A GPS is Assisted Global Positioning System. So now we're back in 2.13.3. A GPS is a handset-based location determination used in wireless networks to get the location of a 911 caller. So a typical A GPS-enabled handset uses a data connection to contact the assistance server in the network for satellite information. So this is an AT&T phone. If I want to know the location of this handset, it's using my data connection to contact AT&T's assistance server in AT&T's network. Okay. The assistance data provides a faster time to the location than standalone GPS can, because the handset's provided with observable satellite and measurement information. But it requires a special chip in the handset to interact with the assistance server in the network. So yes, you need a chip in your phone in order for us to find you with your phone. A GPS can provide very accurate locations in environments with unobstructed views of the sky, but it doesn't function well indoors or in other environments where obstructions might interfere with the ability to obtain satellite signals. So for 911 calls placed from modern smartphones, GPS is one of the many, many reference points in determining caller location. So I'm going to stop there and see who has questions about GPS. Yeah, Kim.
So I had a question. Let me go back to it real quick.
Sure.
Because it was when we started. When you talked about, well, I guess it was right before GPS, I'm sorry, the location services
Uh-huh.
2131, where you talked about, I wondered, why is the privacy higher for 911 than for commercial?
I don't
Okay.
know. Does
Okay.
anybody know? Daryl or
It was like,
Michael
why?
or Connie?
Why should a civilian receive a higher degree of privacy
I'm not
to call
sure.
911?
Well, this is Daryl. I mean, I'm not sure exactly of the context, but generally speaking, when you call 911, you give up your right to privacy.
Right.
So, you know, the goal is to get responders to you as quickly as possible, not so much to keep your information secret.
And so maybe I misunderstood, or I was thinking of that backwards, that there was a higher degree of privacy, that it was harder for 911 to receive the data information than it is for a commercial application, is the way I understood or misread that maybe.
I don't think you misread it, and I don't think you misunderstood it either, because that's what the book says. But Michael's got his hands up.
So I don't know the official answer. Don't quote me on this, but my understanding and my guess is because the 911 system allows for that higher level of confidence, that what should be a more accurate location. Therefore, there's a little extra level of privacy there. But I would say more importantly, it's more about the expectations. If Domino's Pizza sells your location data to one of their partners, that was a commercial entity, a commercial relationship where you may or may not have some right of privacy in your data, but you have given it to this commercial entity. Versus calling 911, that's, you know, certainly you have given up the privacy of your location to me in the 911 center, but I cannot turn around and give that to somebody else.
Yeah, that makes so much more sense. I hadn't gone to that one more step. So thank you. That
Thank you for the phone a friend help, because it didn't make any sense to me either. But that's what the book says, so that's what I put on the slide. Great question. Who else has questions? All right. We're going to talk about uplink time difference of arrival. And it is in the book, and so there's a possibility that it's a test question. So UTDOA, did someone have a question? Okay. UTDOA was the predominant network-based location technology used for wireless 911 calls. It determines location based on the time it takes a signal to travel from a mobile phone to each receiver, called location measurement units. Okay. So using that timing information from multiple LMUs, UTDOA calculates the mobile phone's location using that technique called multilateration. Since it's network-based, it doesn't require the mobile phone to have a special chip. So instead of being handset-based, UTDOA is network-based. It can locate any type of mobile phone on the provider's home network. But it's only available to the owner of the sensor network, which is typically the wireless carrier, because it requires physical access to the network's cell towers, or as they like to call them here, base transceiver stations. That's technical. This technology is not generally available when the user is roaming outside their home network. So the primary advantage is that it has consistent accuracy in all environments, but the disadvantage is that it doesn't work well in areas with sparse cell site spacing. So it's not widely in use today, but it might be used in some cases or areas, and it's still a possible test question on the test. But it's just good to know that that type of location technology is not in widespread use. So then we're talking about indoor location technologies. So the FCC has required wireless carriers to deliver location information for mobile 911 calls for 30 years. But in 2015, the FCC issued its fourth report and order establishing rules and deadlines for indoor location accuracy. In those rules, the FCC deferred adoption of a specific Z-axis metric, citing the need for further testing. So when they issued those rules in 2015, they said they didn't want to say specifically about Z-axis being the height in a building, because they needed further testing. So after the independent entity Testbed LLC conducted that testing, the FCC issued the fifth report and order, which adopted a Z-axis location accuracy metric of plus or minus 3 meters in the vertical plane for 80% of calls made from Z-axis capable devices. So a lot goes into that rule, right? It means that there has to be, the accuracy has to be plus or minus 3 meters in the vertical plane. So right now I'm sitting on the second floor of my house. And if I make a call from my wireless phone, the information about that, the fact that I'm sitting on the second floor, should be delivered to the 911 center 80% of the time. So hopefully I fall into that 80%. And hopefully my handset is a Z-axis capable device. So all of that has to be true in order to meet the rule. The fifth report and order also laid to rest the National Emergency Address Database. So in the last study session, we learned about the NEAD, but they laid it to rest in the fifth report and order because it allows the FCC's dispatchable location requirements to be met by sources other than the NAED. So that means that wireless carriers and other providers can meet that dispatchable location requirement, and they don't have to use the NEAD to do it. The sixth report and order adopted many other things that were proposed in the fifth. So it allows carriers to comply with 2021 and 2023 Z-axis requirements by deploying Z-axis technology to at least 80% of the greater than 3-story buildings in a given area. Okay, so in other words, the carriers could now meet that order by deploying some technologies on the buildings in order to provide that Z-axis information. It added a nationwide Z-axis requirement. So the carriers had to deploy Z-axis technology nationwide by April 3rd of 2025. Now, what I don't know is if that's still accurate and true, or if they've extended it. Obviously, the book published in 2020 doesn't say, so we're not going to go into that because I don't want to confuse you for the test. But that's what the sixth report and order said. And it aligns wireless location accuracy requirements with those rules that govern multi-line telephone systems, or MLTS, and voice over internet protocol by requiring delivery of dispatchable location by January 6, 2022, where technically feasible. So, all that to say that you should be getting Z-axis information in your location feeds at the PSAP. If not now, then soon. As of October 2020, mobile location services are envisioned to be used for indoor caller location with an implementation deadline of April 2021. And these services could be augmented with additional positioning equipment used for 911, such as barometric pressure sensor networks that are not normally used for commercial location services. They can be implemented to support those indoor location requirements. In other words, those carriers could put other sensors into buildings to help locate people on the Z-axis. And this is really beneficial for areas that have multi-story buildings, so that when someone calls 911, it should be able to tell you that they're on the 36th floor of that building instead of having to either get that information verbally or go on a search. So other resources as far as location technologies can be found in section 213.6 in the study guide. And I'll see if anybody has any other questions about location technologies. Fun stuff, right? All right, well, you guys are doing great. So let's talk about apps, shall we? The things that we live on with our cell phones as they relate to 911. So callers expect 911 to know exactly where they are no matter what. All of you taking calls have had that happen probably 10 times a day. What do you mean? You know exactly where I am? Well, no, we don't. And of course, the oft-cited question is, how come pizza delivery can find me but 911 can't? And that question leads to the development of apps for emergency response. Obviously, the public safety requirements for reliability, accuracy, and sustainability far surpass the standards of most commercially based delivery systems. So for example, if I want Uber or Lyft to find me, or Instacart or whatever, right? If they don't find me, it's not generally a life or death situation. But obviously, if 911 can't find you, it could be. So the public safety requirements for all that reliability and accuracy have to be greater than Uber or Lyft. And we've tried to explain the intricacies of 911 call routing and the next-gen 911 architecture. And we have formed coalitions with the inventors of apps that have gained traction in the app space, and dozens more are created all the time. And all of that outreach still comes to the end result of PSAP personnel facing a variety of novel means through which mobile applications present information to 911. All of that is a fancy way of saying that people are constantly inventing ways to contact 911 that may or may not work very well, and that PSAP personnel have to be aware of anyway, just in case they get a notification from them. So until the 911 community can finalize and enforce standards, PSAP personnel needs to stay aware of the ever-changing landscape of technology. But understanding how the majority of apps interact or should interact with the 911 system is essential. So the following slides are going to detail the ways in which apps interact with 911. One is delivery via NENA I3 requirements, okay? These would be apps that generate a call for service to 911 and enter an EZNet via a SIP connection, that's an IP-based connection. Those apps will have the ability to pass more information to the PSAP, but only if that PSAP has the ability to receive and display such information. So right now there's a lot of conversation about how automatic or the telematics, and there's a slide in here about telematics, but there's a lot of conversation about how telematics can get all of the data that's available to them to the PSAP. Part of the challenge is standardizing call handling equipment to be able to receive that data in a standardized way, right? So if those apps can pass that information, that's great, but it does nobody any good if the call handling equipment inside the PSAP doesn't have a place to put that data. If you want to know what standard defines that, that standard is right there on the screen. And it's called the Next Gen 911 Additional Data Standard. So you can dive into that on your own time. If the call flow crosses an IP to CAMA gateway, so if it passes that conversion coming in from IP to legacy gateway, or if there's any intermediary along the call routing path that can't pass on that information, then that information is not going to get to the PSAP. And while this is the preferred method for apps to interact with the 911 system, it's not supported nationwide. So one way of getting apps is delivery via the NENA I3 requirements. Another way is additional data via web interface. And those of you working in a PSAP are probably very familiar with this because you probably use some sort of method of additional data gathering via a web interface. So in this solution, PSAPs can get that additional data from the caller via caller-provided data sets or directing the caller to a web interface. For example, Smart 911, or What 3 Words, or a variety of other options that are available. And many of these solutions are stopgap measures, but they may require the caller to pre-register for the service, or they might only be available inside the PSAP's geographical boundary, which is helpful if they're in your PSAP boundary, but if they travel outside and expect that same service, the next PSAP over might not have that same service, and so it's not a viable solution then. And while that's not considered an app, the application runs within a web interface. It would require pre-installation coordination with individual PSAPs and is primarily a stateless connection. So I guarantee the vast majority of PSAP personnel watching this study session are getting some sort of additional data via a web interface. You can also have delivery via CAMA trunking. So these apps place a call for service delivered via the legacy CAMA trunks. So remember, CAMA trunking is a way of delivering 911 calls in the legacy or analog environment. So the features created within those apps, which could be better location or text to 911 or emergency contact notification, but they're limited by the voice and data paths of traditional wireless 911 traffic, which we're moving away from. Many of those apps have a one-touch feature that dials 911, but it's still going to rely on the inherent location services to produce that phase 2 location. And it's important to note that the features such as the ability to text to 911 are completed via an intermediary that converts that text into speech for the telecommunicator to process. This is not the same as text to 911 solutions that are endorsed by NENA. This is kind of an old school way of apps interacting with 911. You can also have direct connect to a PSAP. So apps that directly connect or route emergency requests to a PSAP via non-emergency numbers. Non-emergency numbers. This method circumvents the 911 infrastructure and doesn't provide reliability, accountability, or efficiencies provided by 911. And there are limitations related to transferability, reliability of the callback number, and accuracy of the location. So apps that do not integrate into the 911 ecosystem can cause all kinds of challenges for PSAP personnel. You can also have a conventional 911 call delivery method via app. So some apps simply place a conventional 911 voice or text call through normal means, but deliver an unusual payload. For example, smartwatches with fall detection. I know that's everybody's favorite. Some mobile phones have a silent 911 feature where a person would place a conventional 911 call that plays a recording indicating the caller cannot speak. This is otherwise a normal 911 call that delivers location through normal means. So you'd still have Annie Alley, but you get a recording saying this person cannot talk right now, and you're supposed to just send help, I guess. Well, I don't know what kind of help. Other implementations place a conventional 911 call while embedding unusual information in the alley. And all of these methods are a natural consequence of legacy 911 systems intersecting with a modern IP-based mobile connected world. In other words, the legacy 911 system has a hard time keeping up with the technology that is at your fingertips every time you pick up a cell phone. And so these stopgap methods keep popping up. So in closing on the mobile-based application topic, 911 authorities need to be clear that apps intended to connect the caller to a PSAP are not the originally intended method of call handling at this time. But it's a reality that PSAP personnel have to be educated about and trained in these alternate methods because they are going to happen as technology continues to evolve. And with the proliferation of public safety broadband networks supporting 3GPP mission critical services across the US, that also means that apps between the PSAP and response organizations, so your fire, your EMS, your law, are most likely going to follow the same trajectory as public apps. So not only do you need to deal with apps popping up for the public, but also for your responders who are also interested in all the shiny new things and ways to communicate. So who has questions about mobile-based applications and 911? You guys are probably pretty familiar with all of that, and now you just have the formal language to answer that and answer your ENP questions, test questions. All right, we're almost done. Hang in there, okay? So GPS-based telematics services. Telematics use a cell device that's embedded in a vehicle, equipped with a GPS receiver, and an interface with the vehicle's computer to communicate. That's how telematics work. So when you press a button in the vehicle, the cellular device dials a pre-programmed number to access what's called the telematics service provider, or TSP. Of course, when everybody thinks about telematics, they're thinking about OnStar. So you push the button and it goes to an OnStar telecommunicator. Once connected, a microcomputer in the vehicle transmits that GPS location data and vehicle identification data. So at the TSP, employees use a GIS-based system to identify the caller's location as well as the applicable local emergency services. And then they call you. That also includes automatic crash notification, or ACN, which automatically places a call to the TSP if the vehicle is involved in a collision. I know you all are familiar with that if you're working in a PSAP right now. This action can be triggered by airbag deployment, seatbelt tensioners, or other sensors in the car. It can be really valuable for collisions in rural areas where there might not be cell service, and it can greatly increase the probability that the occupants will survive the crash, especially if they're unconscious, because those calls get placed even if the vehicle occupants are unconscious. So those in-car sensors can also capture vehicle speed, orientation, like whether or not it's upside down, and other data that can help determine the severity of the crash. So telematics providers have evolved from dialing 10-digit PSAP emergency numbers to more sophisticated 911 interconnections. So today, interconnection via the infrastructure that supports internet telephony or voice over IP service providers enables those TSPs to generate 911 calls that deliver the vehicle's location via ALI. In other words, it can show up in your 911 center as an actual 911 call. So the way that works is the TSP would receive the call and location data from the vehicle. So the agent at the TSP initiates those emergency procedures. The call gets initiated from the TSP office or call center to the provider, which passes the location of the vehicle. The provider uses those same processes used for VoIP service providers. So remember when we talked about VoIP call routing, they use a VoIP service provider to route that 911 call to the E911 selective router or the next gen 911 equivalent. That routes the call to the appropriate PSAP either by location or as directed by the TSP. So an ALI record identifies the TSP and the vehicle's Latin long is delivered to the PSAP via that ALI query. Pretty cool, right? TSPs also maintain detailed PSAP directories as a backup. And the telephone number you generally use to place the call is a 10-digit emergency number in the PSAP. So remember in previous study sessions, we talked about how legacy 911 lines or trunks also had a 10-digit line attached to them. So a lot of times those telematics companies would have those 10-digit numbers and place the calls that way. So it would ring 911, but you might not get any alley information. Those agencies are typically contacted periodically to verify the number to be called in an emergency. And of course, if that 911 interconnection is unavailable, then they pass all that information over to the PSAP verbally. So TSPs allow E911 PSAPs to receive notification and a positive location from crashes very quickly. And although a call from a telematics service providers may not be the first call about a crash, the TSP call usually has a dispatchable location, pertinent information about the incident, and emergency contact information for at least one of the registered owners for the vehicle. So you've got a lot of information that can be gathered through a TSP and passed on to your providers, your responders. So I will pause there and see if anybody has any questions about telematics. All right. You made it to the end. So now I get to ask if anybody has any questions about anything that we went over in the last hour and 15 minutes. Now you know all about how GIS works and how all the different systems can try and find a 911 caller. And you learned more than you ever knew about telematics. You're ready to build a GIS database for your next gen 911 system, right? Well, you're at least ready to take the ENP test. But if you have any questions as you're going through and watching this video, please don't hesitate to contact any one of us on the screen. We are all here to help you, and we would all be very happy to help answer your questions and help you pass your ENP exam. So don't hesitate to reach out. No question is too small. And thanks so much for spending your evening or your time with us watching this video, and good luck on your ENP exam. We'll be back with the next round next week.